In this video, we're going to take a look at section 2.3 on other statistical graphs. So in section 2.2, we looked at one type of statistical graph, which is called a histogram. In this section, we're going to look at a plethora of other types of graphs. These are fairly antiquated, dry, academic type of graphs, but useful. And we're going to make use of some things that we've talked about previously in the chapter. So the first one we're going to look at is a frequency polygon. A frequency polygon, excuse me, is essentially a line graph of a frequency distribution. Each point represents a class with ordered pairs of the form class midpoint for the x coordinate and the frequency of that particular class for the y coordinate. So you're going to plot a point for each class that you have. Lines are then drawn to connect each pair of consecutive points. Lines are also drawn from the first and last point down to the x-axis. And we'll talk about why that is going to be done when we get to that point of the problem. All right, so we're taking each class, graphing it as a point. It's literally like if you took the histogram and you converted each bar into a point right in the middle of the top of the bar. So if you go to the very top of the bar and put a point there at the very middle of the top of the bar and just erase the bar, those are the points of your frequency polygon. And then we just connect the points with lines. All right, so let's go ahead and actually do an example of this. So we're going to go back to the same data that we used in the video for section 2.1 and 2.2, which is the critic review scores for the game Animal Crossing. And I say the critic review scores. I probably shouldn't say that because that makes it sound like it's all of the critics' review scores, which I don't know and would assume is probably not the case. So this is a sampling of critic review scores of the game Animal Crossing. All right, so this is the data set that we've been working with throughout the entire chapter, and we'll probably continue to use it in the videos for the next chapter as well. And this was the frequency distribution that we constructed from that data, and this is in the lecture for section 2.1. So if you want to go back and watch that video, you can see how this was constructed. We want to take this information and draw it as a frequency polygon. So what we need to do, so how do I want to say it? What we need in order to do that is to use the class midpoints for each class as our x coordinates and then the frequencies as our y coordinates. All right, and so we would need to go back to the video for 2.1 to see what the midpoints were, but I think I can remember what they are. This one had a midpoint of 65.5. That's the number exactly halfway in between 61 and 70. This one had a midpoint of 75.5. This one had a midpoint of 85.5. And this one had a midpoint of 95.5. They were all 10 apart from each other. And we're going to pair these midpoints with these frequencies. So our first point is going to be 65.5, comma 1. Our second point is going to be 75.5, comma 11. Our third point will be 85.5, comma 59. Probably didn't pick the best data set because just a large spread of values in the frequency, and maybe not even the spread so much as just having that large frequency. 59 is a pretty big number. I should have picked a data set where the frequencies stayed a little bit lower, or I could have did a better job of constructing the classes so that we wouldn't have so many in one group. But it's too late. So, and I'm sorry, I don't know. I guess I haven't been doing much talking the last couple days, so now my voice is not loosened up. Need to loosen up those vocal cords a little bit. All right, so the last class gives us the point 95.5, comma 36. And so we're going to plot these 4 points on a Cartesian coordinate system. And so that's what we want to do here in this space. And I'm going to do my best to kind of draw this freehand. It's not going to look very nice. Okay, I'm going to try to do that a little bit better. Okay, okay. What can I do? There is a straight line tool. I'm just really kind of being lazy. So let me just do that, and that'll make sure it's perfectly straight. Okay, and then remember for the histogram, because we're kind of working with the same set of numbers, for the frequencies will go on the y-axis. So this is our y-axis, and here we will have the frequencies, which I'll just abbreviate like that. On the x-axis, we're going to have our review scores, and we'll be using the midpoints to plot these points. For each point, we'll be using the midpoint as the x-coordinate. For the y-axis, remember, just like the histogram, we have to start at 0 on the frequencies. Otherwise, we create a misleading graph. Said that kind of funny. And we will be looking at misleading graphs later in this video, so you can see why, if you don't start at 0, why that's going to be misleading. So just take my word for it now, but we will see an example later, and you'll see for yourself why this is really important. But we have to get to 59. And so what we did in the previous video is we went by tens. So I'm going to say that's 10, 20, 30, 40, 50, 60. We have to get up to 60 in order to fit 59 in there. And so this is going to be 10, and this is going to be 30. We'll just kind of label every other one, I guess. All right. And so for the y-axis, for the frequencies, you have to make sure you're starting at 0, but not so for the x-axis. So we're going to, usually the origin would be at 0, 0. Well, we're not going to draw our y-axis at the origin like you would normally see. We're going to scooch it over to where the data actually begins. But we also need to kind of stay a little bit back from where the data begins because of the last thing in the description, which is we have to take that first point, connect it down to the x-axis, and we'll need some space to do that appropriately. And so I'm going to kind of leave a little bit of a gap here and maybe start right here, and we'll let this be our 65.5. And so I would say halfway here, this is going to be 55.5, and you'll see why that's going to be important in just a second. So we have 65.5, this will be 75. I'm going to try to keep these gaps the same. I'm trying my best. 75, or sorry, that's 75. This will be 85.5, and then another same space over. That's going to be 95.5. I'm not going to write those in because it's going to get too crowded. All right. So let's plot these points. We had 65.5 comma 1, which is going to be way down here, which is also going to kind of make it hard to do the last part of the problem. It's not going to look as interesting as it probably should, as we would like it to. Maybe, and again, it's not maybe what we like or what it should look like. I mean, it's going to look the way it's supposed to look, but it's just going to be hard to really appreciate because of the example that I have here. So 75.5 comma 11, that's going to be just a hair above 10, which will be about like right here. Now this is kind of nice because I've done examples in the past where they just kind of go along almost a line. And that, again, that can happen with some data, but it doesn't really give you a good sense of what these frequency polygons can look like. So this is going to give you a pretty dramatic idea of what this can look like. So 85.5 comma 59, we get a huge jump here. It's almost practically at 60. And then it's going to drop back down, but not quite as dramatically, to 36 for 95.5. It's going to be about halfway between 30 and 40, so about right here. All right, so we're plotting all these points, the points that we outlined here. I just plotted those points here. Then to make it a polygon, we connect each consecutive pair of points with a straight line. So again, I'm going to use my straight line tool to make sure this looks right. And so let's go ahead and start with this first point. So here's two consecutive points. Remember, consecutive means one right after the other in a row. We want a straight line connecting these 2 points. All right, so there we have that. Then this point and this point are 2 consecutive points. So we want a straight line connecting these 2. So you get this really dramatic increase here. Okay, I guess I should redraw that. I was just looking. I'm going to redraw that point. I'm not quite above the 85.5. I'm a little bit to the left there. So let me redraw that point, and we'll go ahead and switch it back to red and try that again. I was more worried about getting it near the 60 that I wasn't really paying attention to. Was it lining up with the 85.5? All right, so let's try redrawing that. Go back to the line drawing tool. All right, and then connect it to that point. All right. Oh, I keep missing when I lift my pen off the pad, it jumps a little bit. So let's see if I can account for that. Okay, that looks pretty good. then these are 2 consecutive points. So we want to connect those with a straight line as well. And we get this kind of interesting zigzag type of graph, which really visually demonstrates the dramatic jump, because it is pretty dramatic, right? In one class we have 11, that's from 71 to 80, and then it jumps up to 59 for 81 to 90. And so that is a really dramatic jump, and we can see that in the table, but it's nice to also have a visual representation of that jump, so we can see how dramatic of an increase it was as you got to those higher ratings for the game. All right. However, a polygon is a closed shape. This is not closed. It's open. It's just a line, and we have these openings here. It's kind of a small opening over here, but it's not closed down with the x-axis. So to make it a polygon, it has to be contained. It has to be enclosed in some way. So we want to tie the ends down to the x-axis. But we want to do it in a symmetric, I don't know if symmetric's the right word, but in a way that's consistent with the design of the rest of the graph. And so that's why I marked 55.5 here, because each of these points are spaced out by 10 on the x-axis, because that was the class width. We want to respect that width as we tie this graph down to the x-axis on the ends. And so even though it's not a point in my frequency distribution, I'm going to put a point here on the x-axis 10 away from the first point. So it's the same spacing, and then draw a straight line to connect the first point for my frequency distribution down to the x-axis. So like I said, I was kind of disappointed because it's already so close to the x-axis, you're hardly going to even be able to see that line. But we also need to do the same thing on the other end. And I didn't mark this point, but this is 95.5. I need to go another 10 to the right, which is going to be, I'm still on the line drawing tool, which is going to be 105.5. So we want to respect that same spacing that we had throughout the entire graph, and then mark a new point here on the x-axis as well, so we can tie the graph back down to the x-axis over here. So let's go ahead and do that. All right, so we're going to go from this point here, straight line. Make sure you draw these straight from one point to the next, and we get that line. And so this is what the frequency polygon looks like for the Animal Crossing data that we've been using. All right, so make sure you're tying it down to the ends. Make sure the spacing you use to tie it down on the ends is the same as the class width, which dictates the spacing between all the points throughout the entire graph. It just makes it look nicer that way. Plus, that's what we need for it to be correct. Now, I'm sure on your homework on my stat lab, it's going to be multiple choice, but I would, again, encourage you on the homework to try to draw these by hand first before making your multiple choice selection, because that is what you will be expected to do on the exam. Your exam will not have multiple choice graphs. It's going to be on paper, and it's going to say, draw this frequency polygon if that problem happens to be on the test, and you just need to know how to draw it by hand. Use the midpoints and the frequencies, plot those as points, connect those points with straight lines, and then be sure to draw the endpoints down, connect them down to the x-axis with more lines. All right, so that's a frequency polygon. That's what that looks like. The next thing we want to look at is a relative frequency polygon, which is just a frequency polygon, but with the frequencies replaced by percentages of the total number of data values. So it's very analogous to, we had frequency distributions, and then we had relative frequency distributions. And the thing about a relative frequency polygon is that the graph is not going to change. It will look exactly the same. What is going to change is the y-axis. Instead of it being, I don't know, now I'm thinking about it, would it look different if you change it to percentages? It should, the relative distances should still look the same, I would think. But what's going to change is the y-axis is going to be percentages instead of actual values. All right, so let's go ahead and draw that. So let's see. I guess this will be a good test, right? So my inclination is that really what I could do is copy and paste the graph that we just did, erase the y-axis numbers, replace them with percents. But maybe not. Maybe when you have percents, maybe it kind of changes the way the graph looks. So let's go ahead and do this one by hand and see if the percents make the graph look any different. All right, so here is the relative frequency distribution that we constructed in section 2.1. So if you go back and look at the video for section 2.1, you'll see a construction of this table in that video. I'm just copying it over for use here. So I want to rewrite this table as a frequency polygon, but I will be using the percentages. And what I'm going to do, because for graphing, I mean, in the table we did in the video for section 2.1, we kept the percentages to 2 decimal places. Just because I was afraid if you rounded it off, it would round back to the original number, because our total number of data values was close to 100. So if you have exactly 100 data values, the frequencies and the percents are identical, right? If you have 100 data values and 15 of them are in this class, that's 15%. And if 20 of them are in this class, that's 20%. If the number of data values is 100. We had 107, which is really close to that. So I was worried if I rounded, it would look exactly the same. So I kept 2 decimal places. But as you can see, if you do round, it's not exactly the same, right? This class had 11 data values, but as a percent rounded, it's 10%. So it's slightly different. This one actually is fairly more dramatic. There was 59 data values in this class. As a percent, it's 55% when you round it. So for graphing, it doesn't really make sense to keep these 2 decimal places because my graph is not going to be that precise. I'm going to round it, and that's going to make it a little bit easier to graph these numbers. So it's the same x coordinate that we're going to use. Whoops, still using the straight line tool. Let's switch it. We're going to use the class midpoints. We have 65.5, comma, but this time we're going to use the percent, 1%. Here we'll have 75.5. Whoops, got a little bit ahead of myself there. And then we'll have 10% here. Here we'll have 85.5, comma, 55%. And here we'll have 95.5, comma, 34% when you round that one. And so we'll plot these points and then do the same thing we did on the last graph, connect them with straight lines, and then tie the ends down to the x-axis. Okay, so let's see how this is going to look here. So this time I'll use the straight line tool for both axes just to make it look like it's supposed to look. We will have the relative frequencies here. So relative frequencies, which is percents. So if you want to write percents there, whatever, that's fine. And again, we have to take into account the number we need to reach, which is 55%, right? That's how high up it's going to go. So again, I don't want to go by 1%, 2%, 3% because I won't reach 55% by the time I get here. I need to make sure it fits in the space that I have. So I'm going to go by 10% again, right? So this will be, I say again, we went by 10 last time for the frequencies. We'll go by 10 again for the percents. That's what I meant to say. So this is 10%, 20%, 30%, 40%, 50%, 60%. All right, 60%, 40%, 20%. All right. And then on the x-axis, again, it's the critic scores, the review scores. I'm trying to think of what I called it last time. Okay, review scores. And we'll do the same thing. We need to leave the same amount of space. Well, maybe I could just say, let's just do this. That's 55.5. This is 65.5. And then we'll have 75.5. 85.5, 95.5, and then remember we also needed to go a little further to 105.5 when we tie it down to the x-axis at the end. And so we'll plot these points. So let's see if the graph really basically looks the same. And so we have for 65.5, the percent was 1%, which again is going to be really low, close to the x-axis. For 75.5, it was at 10%. So that's a little bit different, right? So maybe the graph's going to look a little more smushed. So maybe I really can't just copy and paste it because as frequencies, we get, I don't know, it's just because I'm using the same scale of 10 on the y-axis. As frequencies, the numbers are a little bigger than they are as percent. So while I think relatively speaking, the graph's going to look about the same, it'll be maybe shrunk down in this direction. All right. So 85.5 comma 55, that's going to be halfway in between 50 and 60, which is going to, let me make sure I line up with 85 this time. And then for 95.5, we're going to be at 34, which again is pretty close to between 30 and 40, which is going to be about right here. So maybe right there. All right. So those are the points for my relative frequency distribution. And then we connect these points with straight lines. So straight line connection there. A different straight line between these 2 points, and a different straight line between these 2 points. I kind of missed the mark there, but I'm just going to let it go. And then we need to tie it down to the ends. So we're going to tie it down to the x-axis here. I said that kind of funny a moment ago, but we want to tie the graph's endpoints down to the x-axis. That's what I meant to say. So let's change the color back, go back to straight line. All right, and so there's that one. You can barely see it. And then we'll have one right here. So it looks roughly the same as it did the first time. I mean, if you go back and compare the two graphs, they kind of have the same shape to them. All right, so that is a relative frequency polygon. I've spent 20 minutes on frequency and relative frequency polygons, so I'm ready to move on. There's several other kinds of graphs that we want to look at. An O-hive is essentially a line graph of a cumulative frequency distribution. So if you go back to section 2.1, we talked about frequency distributions, relative frequency distributions, and then cumulative frequency distributions. So all three of those types of frequency distributions can be graphed as line graphs. And so that's what we're going to be doing with the O-hive. We're going to be graphing a cumulative frequency distribution as a line graph. Each point represents a class with ordered pairs of the form class boundary, comma, cumulative frequency. Now the class boundary, I should be more specific here, because remember there's really two class boundaries. There's one before the class, there's one after the class. So I guess we could maybe describe them a little bit better as the lower class boundary and the upper class boundary, right? And for each class, we want to use its upper class boundary. I'm still using the straight line thing. Let's switch it. We want to use the upper class boundary here. Okay. The first point should start at first class boundary, the first upper class boundary, comma 0. Is that right? Maybe it's not the upper class boundary. Okay, now I'm questioning myself. It's been a while since I've looked at this content, and I didn't really research this. It should start at 0, so I'm going to say yes, but this will be the first lower class boundary, the beginning class boundary that you start with. And it's going to start at 0 because you don't have any data values yet. And then from there, we're going to see how it grows. So that's what's interesting about the O-hive, is you can see how the graph changes as you add more data values to it. Where is there a large increase? Where is there not? Where is there maybe a small increase or no increase at all? But it starts at 0. I do know that for a fact. What we don't do is we don't tie the other end down to the x-axis. So the O-hive will start at the x-axis at 0. But it grows and grows and grows, and then we just leave it hanging up there. We do not take the end of that and tie it back down to the x-axis. So that's going to be one major difference between an O-hive and a frequency polygon. So lines are then drawn connecting every pair of consecutive points, just like a frequency polygon. The last point, however, does not connect back to the x-axis. Okay, so sorry, I had a little bit of a mind fog there for a second, but now I feel fairly confident that I'm describing this properly. So, okay, so let's take a look at the cumulative frequency distribution that we constructed in section 2.1 for the Animal Crossing data. It looked like this. So we need to recall our class boundaries, and the class boundaries, like for example here, I changed this for the cumulative frequency distribution because this 12 represents all the data starting from the beginning, from 61. But remember, the original lower class limit there was 71. So the boundary there is 70.5. That's the upper class boundary for this particular class, which is what we want to pair with this cumulative frequency. So we will plot the point 70.5, comma 1. Here, the next class boundary, the next upper class boundary is going to be 10 away, so it'll be 80.5. Comma the cumulative frequency, which is 12. Here we're going to have 90.5. And the reason we want to use the upper class boundary is because we want to clear that entire set to associate that with the 71, right? Because by the time you hit 90, you have found 71 of your data values. But you have to be clear through 90 before you hit that 71. So we want to use the upper boundary. So by the time you're at 90.5, you've gone through 71 of your data values. That's what we are asserting with this particular point. And then here we're going to have the last class boundary, 101.5, and all the data values. By the time you get to the end of your frequency distribution, you've hit all your data values, all 107. So these are the points we're going to plot that are associated with each class. However, we want a starting point. So as I mentioned, you want to use the first class boundary, which is the one that occurs before the frequency distribution even starts, which is going to be 10 before this one, which is going to be at 60.5. And we're going to start that one at 0 because it's the beginning. We haven't encountered any data values at that point. And then we encounter 1 by the time we get to 70.5. We encounter 12 by the time we get to 80.5, et cetera, et cetera. And so these are the 5 points that we want to graph for this frequency, or for this O-hive, excuse me. Now, notice we use all of the class boundaries in constructing the O-hive, right? We use the one before the frequency distribution as our first point. We use the one at the end of the frequency distribution as our last point, and then we use all the class boundaries in between for a particular class. All right, so let's go ahead and plot this one. Again, we're going to have to do it by hand. Sorry you have to sit there and watch me struggle with putting this together, but there's our y-axis, there's our x-axis. Let's switch back to that. So here we're going to have our cumulative frequencies. So this is our y-axis. Cumulative frequencies, which this is even worse than the previous ones. We have to make sure we can hit 107. And so we probably should go by 20s at this point, I feel like, in order to make it fit in this space in a reasonable way. So I'm going to say that's 20, 40, 60, 80, 100, 120. All right, so there's 120. This is 80. This is 40. So the lines all represent, I don't know why my 4s do that. Like whenever I draw a 4, I don't know if I'm just going too fast, but when I go to start this line, because I do it on like 2 separate strokes, when I go to start this line, it connects it back to the beginning of the other one I drew. And so I get this kind of, it looks like a 9 instead of a 4. It's done that multiple times. It's starting to bug me. All right. So we can now make sure we fit 107 in here. And then for the x-axis, again, these are going to be the review scores. But we want to mark the boundaries, not the midpoints this time. And so we're going to start with, and we don't need to leave any space before or after this time. We're going to start with 60.5. That'll be at 0, right? The frequency for that will be 0. And then we'll go 70.5, 80.5, 90.5, 100.5, right? And that's going to give us our 5 points. So we'll plot these points. We start at 0, 60.5, comma 0, 70.5, comma 1. So again, kind of a tough one to deal with when we're drawing this one. 80.5, comma 12, right? So this is 20. Remember that first mark is 20. I almost went above it because I thought it was 10 for a second. It's going to be below it. It's going to be pretty low still, right? So a little more than halfway, right? Because, you know, halfway would be 10. So I'm trying to draw a little more than halfway. So that's supposed to be 12. And then for 90.5, we get this huge jump. It jumps up to 71, right? So this is 60. That's 80. 71 is going to be about halfway, a little bit more than halfway between 60 and 80. Oh, my eyes are going cross-eyed here, it feels like. All right, so about right there. Again, another reason I'm drawing these by hand is so that you can see the quality. This is the best quality I could expect on the test, right? The best I can do is the best I can really expect from you. And some students will exceed that expectation and draw much nicer graphs because they're just better at drawing, better at, you know, lining things up than I am. Other students may do a little bit worse, and that's still okay. It might not look as nice as this, but still, you know, have all the right things in it that I don't have to take any points off. So I just kind of want you to see it doesn't have to be perfect. This definitely is by no means perfect, but you just want to make sure you get the right characteristics in the graph. and that you're putting, and show that you're putting some effort into making the graph look the way it's supposed to look, even if it doesn't come out perfect. Right, and then 100.5, 107, right? So this is 100. 107 will be not quite halfway between 100 and 120. Oops, went too far. All right, so it's going to be about right here, maybe. Again, it's an estimate. We have to kind of estimate those points. Now we're going to connect these consecutive pair of points with straight lines, just like we did with the frequency polygon. So, whoops, I thought I had the straight line until I got to switch over. All right. Okay, so there's our first line. A little bit more of a modest jump there, and then a huge increase from this class to this class. And then another increase, but not quite as dramatic. So you can see, based on the slope of the line, what the increase is going from one class to another, right? And this line is the steepest one. It has the biggest slope, and so that indicates the biggest increase. This line, the slope is still fairly sizable, but not as big as this one. So it's another jump, but not quite as big as this jump. This line is a very small slope. It's very, very flat. And so that indicates there's not much of a jump there at all. So that's kind of how you can interpret an O-hive. You do not connect this down to the x-axis. You leave it up here. All right. Okay, let's move on. So a stem and leaf plot is a table where the data is separated between two particular place values. Where you do that separation kind of depends on the data that you're dealing with. Most common, I don't know, maybe most common's a misleading thing to say, but what we're going to be doing with our data anyways is we will be separating the tens place from the ones place. And that is a pretty common place to separate your data values. The digits at a higher place value become the stems of your stem and leaf plot. So think of it like a plant, right? That's the analogy here. And, you know, stems on a plant kind of stick out from the trunk, if you will. And then so think of the trunk maybe as your, data set. I don't know if that really fits the analogy very well, but you have your stem, and then from the stem, leaves can grow. You can have multiple leaves coming off of one stem, right? And so that's what's happening here, is that we're going to think of the digits at a higher place value as our stem, because it's the same for several data values, right? So if you think of 80, 81, 82, 83, 80, the 8 in those numbers is the same for all those numbers, right? 81, 83, 85. The tens place is the same in each one of those cases. So that's like our stem. It's the same thing. And then there's different leaves. There's different data values coming off of that 80's place value. 81 gives us a leaf of 1. 83 gives us a leaf of 3. The stem is still 8 in both of those cases, but we have these two different leaves. So we're going to think of the ones place as our different leaves that are connected to that stem. The digits at a lower place value become the leaves and are written as a list in the right-hand column, but you do not write each one just once. So if you have like 85 and then 85 again, 5 will be a leaf twice. You need to preserve that data value. You can't say, oh, there's 2 5s, I'll just write it one time. Then the stem and leaf plot only shows that data value once when it actually occurred twice in the data set. And so stems are not repeated. We take advantage of the fact that those stems are shared in common among multiple data values, but the leaves have to be repeated to account for all the data values that are actually in our data set. So the leaves are written in a list in the right-hand column with repetition if necessary. So let's take our Animal Crossing data. I thought I copied it here again. I guess I didn't. And let's write the Animal Crossing data as a stem and leaf plot, or sometimes it's just abbreviated to a stem plot. So I'm going to show you how to get started on that process. And then I'm going to pause my recording and just finish it without making you have to watch me go through all 107 data values in this way. But let's consider some of our data values. Now, some of these are repeated multiple times, and I will make sure the leaves for those are accounted for. But for example, well, maybe we shouldn't start with 100 because that one's kind of a little bit of a weird one. But let's start with we had a lot of data values in the 80s. Okay, that was my straight line. I keep messing up, not switching back. So for 80, for example, we are going to split this data value between the tens place and the ones place, right? And so 8 will become my stem and 0 would be the leaf, right? And I don't think there were other data values in the 80s besides 80 itself. So those review scores are a little weird because like they tend to be 80s or not, like they seem to be multiples of 10 in a lot of cases. I think there was some other ones. I don't know, let's go back and look. Was there something else besides, was there something else besides 80 that's in the 80s? I haven't. Okay, look, there's an 88 here, all right? So let's consider that data value as well, 88. Okay. So if you think of 88, that's another data value we had in our data set. We're going to split it in the same place between the tens and the ones place. 8 is again a stem. So we're not going to repeat that because we're just going to write the stems one time. But this time the leaf is 8. So in my stem and leaf plot, I will have the stems in the left-hand column, the leaves in the right-hand column. Now we do have one data value in the 70s, so I'll go ahead and put that there. And so this represents all the data values that are in the 70s by having a stem of 7. A stem of 8 are the data values in the 80s. And so what I would do with these two data values to plot them, if you will, in my stem and leaf plot is to take the leaf part of it and start listing it in the leaves column. So we have 0 as a leaf for this data value. So I'm going to put a 0 here, comma. We have an 8 as a leaf for this particular data value. So I'll put an 8 here. And you just continue so on and so forth. If I had another data value that was at 80, the leaf there is 0. And so I'd put another 0 in the leaves column. And so when you look at this chart, you put the digits back together again. So when I look at this, I see 80, 88, 80, right? Those are the data values that I'm reconstructing when I look at this chart, which is one interesting thing about the stem and leaf plot is that you maintain the original data set. You can always reconstruct it from the stem and leaf plot. So I'm going to go through all 107 data values and put them in this stem and leaf plot. I might redraw it to make it fit because there's a lot of data values to deal with here. And then I will resume the recording and you can see the final product. But this kind of gives you an idea of how the process goes. For 70, we had one data value at 70. We split it there. 7 becomes the stem, 0 becomes the leaf. And that's all you're going to see in this particular row. But we'll also have 9 as a stem. And this one's a little awkward. And I was going to do this one first, but I skipped it. 100, again, we have to separate it at the same place. So we're going to separate it from the tens place from the ones place. And so our stem in this case will be 10 and the leaf will be 0. And so we'd have this, and that would be 100 right there, right? 10 is the tens place. Again, usually in the tens place, you can only have 0 through 9, but for this stem and leaf plot, we'll think of 10 as being in the tens place, and then 0 in the leaves in the ones place gives us a leaf of 1. I'm getting all my numbers scrambled up. 10 is the stem. We'll think of 10 as being in the tens place. 0 is the leaf because 0 is what was in the ones place. All right. So now I'm going to pause, finish the stem and leaf plot, and then you can see what it looks like. Okay, well, I don't know if you paused the video and maybe tried to create the stem and leaf plot yourself. And maybe this is not a good data set for a stem and leaf plot because there was a lot of data values in the 90s. And it became pretty challenging to even fit it on my screen. So it's quite a large set of data. So there might be some limitations to the usefulness of a stem and leaf plot depending on your data set. What you see on the screen is not the complete product of the stem and leaf plot. I realized after adding several zeros here that I'm not going to have enough room. And then, I was trying to think, well, there's 59 data values in that one class, so I need to make sure I have at least enough room for 59 data values, and this wasn't going to cut it. Excuse me. And so I copied and pasted this to a new screen and moved it all the way over to the left-hand side. And I thought, oh, surely this will be enough. But it pretty much wasn't enough, and I had to really squeeze some numbers together to get it all to fit. And so it's going to look pretty horrendous. I'm just kind of warning you what you're about to see is not going to look really great, but it's the best I could do. And so here it is right here. So this is our stem and leaf plot, for better or worse. And you can see that in the 90s, there were a lot of data values and it stretched all the way across the screen. And this is where I'm really unhappy with the way it turned out, because I really had to like write these zeros fairly small relative. Like you can see here, there's pretty generous spacing, maybe a little bit too much even. But then here I'm really having to like squeeze them all together, and especially like at the end. And that's something you really don't want to be doing. So what's so cool about the stem and leaf plot is several things. It's just such a clever way of organizing the data. For one thing, as I already mentioned, you can recover the data set. It won't be in the same order as you processed it, but you can recover the data set from the stem and leaf plot, right, by putting the numbers back together. And so here, I know this was a 70. This is an 88. That's an 86. That's an 85. And so I can put all the numbers back together, retrieve all 107 of my data values from this stem and leaf plot. It's also kind of like a frequency distribution. Even though, especially for the 90s, you kind of don't know what the frequency is here, you can see it's a lot bigger than the other groupings. Now, this isn't exactly a match to the frequency distribution that we created earlier, because we didn't do it exactly 70s, 80s, 90s, hundreds. We did 61 to 70, 71 to 80, 81 to 90. And so the 90s were counted with the 80s. The number 90 was counted with all of the 80s. Whereas that did not happen here. This was 90 through 99 here. This is 80 through 88, or sorry, 80 through 89. And so it's not exactly the frequency distribution that we did, but it's like a frequency distribution. And if you think of it as classes. And the other thing that it's like is it's like a bar graph. So actually I'm going to go ahead and try to do this. It's not going to fit on my screen because of how wide it is. But if you turn your head sideways, now it's going to be maybe opposite. You know, I'm looking at my camera, though it's kind of flipped around. But if you turn your head sideways, you can think of these as bars, right? If you want to look at it like this is a bar here. And so it's kind of like a bar graph. However far the numbers extend out, that's the height of the bar, right? And so this is a very badly drawn set of bars, but you get the idea. So you can kind of think of it as a bar graph, right? How far the data extends to the right is an indication of the frequency of that particular group. And so what I want to do is try to turn it sideways here so you can kind of see it as a bar graph as well. So let me copy the whole thing if I can. And then I'm going to I think I can rotate it if I... No, that did not. Oh, I just copied it. I don't want to copy it. And I just undid the copy. I want to say I saw once upon a time that I could rotate this thing, but I'm not. Oh, it's over here. Here we go. Well, that's kind of weird and kind of cool. Okay. So now you can think of it as, I wish I could zoom out or something, but I really can't. But now it's like a bar graph, right? And so here's your classes. This is your frequency, and however far the numbers extend is the height of your bar. Right? And this one goes way, way high up compared to the other ones. So that's what's really cool about a stem and leaf plot. It's one of my favorite types of graphs. It doesn't always work for every data set. Now this one was somewhat ideal because there was an easy place to split the numbers between the tens and the ones place. That was pretty obvious given the numbers we were working with. But if you had numbers that were in the thousands and the hundreds and the tens, there's not really a clear, good place to split the data up, right? If we had like review scores of like 978 and also review scores of 310 and also review scores of 95, with numbers like that, a stem and leaf plot doesn't really work if they're all bunched together like that, because where do you split it? At the ones and tens place? Do you split it between the tens and the hundreds place? It's not really, there's really no good place to do it. And also maybe from this exercise, I'm learning maybe the size of the data set also is a limitation. So if you have like over 100 data values like we did, stem and leaf plot gets a little bit tedious to put together and maybe not as useful. Now this interpretation, I also wanted to point out, only really works if the numbers are equally spaced out throughout the entire thing. Now, I don't feel like I did. I don't think I can flip it back the other way. I guess if I undo it, yeah, okay. Oh, wait a minute. Oh, that did not work the way I hoped it would. Okay, I can't undo it because then things get broken, it looks like. All right, but what I tried to do, if you kind of look sideways here, is I tried to line the numbers up as I wrote them. Now, they do get more squished together here, but I still kept the alignment the same throughout. And so whatever, like if this is the 20th data value here, it should also be the 20th data value here, which should also be the 20th data value here. So these should, and it looks like I'm getting a little bit off the mark there as well, but like here you can see there's a pretty good line. So when you're writing your stem and leaf plot, something I look for when I'm grading it is, are you evenly spacing out the numbers? So what you don't want to do, maybe I should show you an example of what you want to try to avoid, is if you do like a stem and leaf plot like this, and you have, 0, 0, 5, 7 here, let's say, that's 80, 80, 85, 87. But here you have 90, 90, 91, 93, 95, 97, 98, let's say. Notice I'm squeezing these numbers together more than I squeezed these numbers together. And so you lose that visual aspect of the stem and leaf plot when you do this, because this has a frequency of 4, whereas this has a frequency of 7, and yet they reach the same width in each case. And so that you want to avoid. And you avoid that by making sure that when you're writing the numbers that they line up. The first values for each leaf are lined up, the second values are lined up, and ideally the spacing should be equal each time you write a number out, which again I didn't do in my example because there are so many data values. I had to squeeze them together, but not even that. I'm not the best at doing that, obviously. So, but make an effort to at least make sure the values are lining up, even if the spacing doesn't stay the same throughout. But again, if you want to do it correctly, then you want to space out the numbers evenly all the way through. That's the proper way to do it. Okay, so this would be bad if we did our stem and leaf plot like that. Because we've shoved those numbers together, we lose that aspect of the stem and leaf plot. I chose not to use commas because, again, so many data values, the commas were just going to make it even more messy. Sometimes you'll see commas used in a stem and leaf plot. And the other thing, which I'm not 100% sure on, is I did not put my values in numerical order. You'll see a lot of stem and leaf plots where they go in order. All the zeros go first, all the ones go second, all the twos go next. I'm not sure that has to be the case for the stem and leaf plot to work. As I said, it checks all the boxes, hits all the marks without it being in order. You can still retrieve the data set. It still functions as like a bar graph. It's still kind of like a frequency distribution. But you'll notice on the homework, especially when you look at the answers or the multiple choice options, they've rearranged the numbers so that they're in numerical order. So I won't personally require that, but I'm not sure. Maybe I'm wrong for not requiring it. So if you take another statistics class, or if you're teaching this topic to somebody else, just be aware that maybe it's a requirement that the numbers should go in order too, but I'm not 100% sure on that. Okay, so let's take a look at another one. We've spent a long time on those few graphs, and I'm sorry, I get a little bit verbose in my explanations sometimes. Now this is one that I'm not as familiar with. There's so many of them that in the past, I kind of focus on the few that I think are most relevant, most connected to what we've already done, and I ignore some other ones. And the dot plot's one that I've tended to ignore. A dot plot is a graph along not an x-axis. A dot plot is a graph along an axis, which is really going to be the x-axis, with data values represented as points. And this is where the dots come in for the dot plot. Dots representing equal values are stacked. So if you get the same number twice, you stack the dots above that particular number on the axis. So maybe for this one, I'm not going to completely construct the dot plot for this data set, but this is what it would look like. This is what it would start to look like. So you have an axis that looks like this. And along this axis, it's like a real number line. You'd have all your numbers. So you'd have like 70. Oh gosh, I'm making the same mistakes over and over. 70, 71, 72. Then you'd have 80, 81, 82. I'm just going to mark the major numbers here. And then, for example, so I counted this for the stem and leaf plot. I can't remember how many there were to begin with, though, but there was a bunch. There's like 11, I think. 11 100s in a row. And so each of those 100s would be represented as a dot here. So I put a dot just above the axis over the 100, and that dot represents a value of 100 in our data set. But we had 11 of them to start the data set out, so I would have to do 11 dots stacked on top of one another. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then we had a bunch of 90s too, right? We had 90s, I don't know how many, we had a bunch of them in a row in that first row of data. And again, you would want these dots to be evenly spaced out. I maybe didn't do a good job of that here, but the height of the dots should give you an idea of the frequency of that particular data value in your set. We also had we had like one at 92. We'd have one dot here. We had a few at 95. 1, 2, 3. Let's say we had 3 of those, right? So your dot plot would kind of look like this. And so that's an example of what a dot plot looks like. I'm not going to finish doing this for the rest of the set, but that gives you an idea of how a dot plot works, right? A scatter plot is actually a very important concept in statistics, and we will be using scatter plots variously here and there throughout this course. So I want to make sure to talk about it here, but it's not actually relevant to the Animal Crossing data because you can only do a scatter plot when you have paired data from 2 different sets. So an example of this that I like to give, even though I don't have actual data for it because it's kind of hard to come by, but the amount of time you spend studying for a test and the grade you get on that test. That's 2 different sets of data, but they're paired, they're linked, right? The number of hours you spend studying, because it's the same student, right? A student spends X hours studying, they get grade Y on their test. This student spent Z hours studying and they get grade B on their test. I don't know, I'm trying to think of a letter to use there, right? But the pairing, they get paired together because both of those sets of data are connected to the same person. And so we can look for a relationship. Does the number of hours you spend studying affect the grade that you get on the test? And a scatter plot would help us determine if that relationship exists. And I would like to think that it does. The more hours you spend studying, the better your grade would be on the test. That's what I would hope the data would show. And that maybe at some point there's diminishing returns, right? Somebody that spends 10 hours studying versus somebody that spends 12 hours studying, maybe their grades aren't going to be that much different. But somebody who spends 1 hour studying versus 7 hours studying, I would hope there's a pretty big difference in the grade that those students get. All right. So each point represents a data pair. So you would take the number of hours a student spent studying, the grade they got on their test, pair those together as a point, an X and a Y value, and then plot that point. And that's all you would do. No lines or curves are drawn to connect these points. It's just going to be a collection of points from this paired data. But while we don't draw lines to connect the points, we do look at the trend in those points to make interpretations on the relationship between the 2 data sets. So interpretations about the relationship between the 2 variables can be found by looking for general trends or patterns in the points. All right. So let's see. I should have an example here. All right. So here's an example of what a scatter plot would look like. Here we're looking at waist circumference in centimeters versus arm circumference in centimeters. And there does appear to be a positive trend in that it seems to be the case that as somebody's waist circumference increases, their arm circumference also increases, right? So that there's not a perfect line here, but the points seem to be following that particular trend. The higher up this one goes, the higher up this one seems to go as well. And so you could sort of, make the prediction of if somebody has a waist circumference of 120 centimeters, it looks like their arm circumference would be somewhere in this range right here between, 37 and 40, somewhere in there. Whereas if somebody has a waist circumference of 80, it looks like their arm circumference is going to be somewhere between 25 and 30, right? But it goes up. The bigger the waist circumference, the bigger the arm circumference is what it seems to be. All right. Here are some other types of graphs that I'm not going to dig into any detail, but you might come across them in your homework, and I think you should take the time to explore what they are, try to understand what they're trying to tell you. Maybe not worry so much about having to construct this type of graph. I don't know. I guess if they ask you to do it on the homework, it could possibly show up on the test. But I tend to focus on the graphs I did earlier. The ones that I constructed for you on the video, those are the ones I might be more likely to ask you to construct on an exam. So we have time series graphs, which are graphs of points showing data that has been collected over time, with points of the form the time they were collected, comma, whatever the data value happened to be. And so you can look for changes in the measurement over time. And you connect the points, the consecutive points, with lines. Bar graphs are graphs that use bars of equal width, just like a histogram, to show frequencies, but of qualitative data. So qualitative data, if you'll remember from chapter 1, is data that is descriptive. It's not numerical. It's not a measurement. It's a descriptive data like colors or labels of some kind, right? And so you could do a bar graph with this is how many red cars there were, this is how many green cars there were, and show the number of each with a bar graph. Pareto charts are graphs that are bars as well for qualitative data, but the bars are arranged in descending order according to frequency. So you start with the highest bar first, then the next highest bar second. So it's just like a bar graph, except that they are ordered from highest to lowest. And then we have pie charts, which are graphs depicting qualitative data as slices of a circle in which the size of each slice is proportional to frequency count. Like I said, you might see some of these on the homework. They might ask you to interpret some of these graphs. You have to look at it and try to estimate, well, what's the frequency of this particular category, based on the chart that's given. I don't know, maybe we'll see an example here. I can't remember what examples I put at the end here. Before we get to some examples from the homework, the last topic in this section are misleading graphs. And this is going back to what I talked about at the beginning of the video, that whenever you're presenting a graph involving frequency, you want to start with 0 at the bottom of the graph. You don't want to jump up to where the frequencies are occurring. And this gives you a good reason why. So this is not a histogram. This is a bar graph, right? Because we're talking about qualitative data here. These are types of cars, not colors this time, but types of cars. We have the Honda Civic, we have the Chevy Aveo, and the Toyota Camry. I'm having trouble talking today. Sorry about that. All right. Now you look at these two graphs and you say, oh, they're two different graphs. No, they actually aren't. It's the same exact graph. And this is why it's misleading to chop these bars off at some other value other than 0, right? This graph starts at 0. This graph starts at 30. So what's really going on is there's a slight difference in these bars. We can see it's slight when we look at the more truthful graph, right? The one that's not misleading. We can see, yes, the Honda Civic is higher up, but not by much compared to the Chevy and the Toyota cars that are given here. What this graph has done is zoomed in. It's starting here, right? It's starting at 30. So it's like taking this graph and zooming in at 30 and just focusing in where the difference is occurring. And so it amplifies the size of those differences when there's really not that much of a difference if you zoom out and look at it relative to 0, right? So that's why you don't want to start at a frequency higher up than 0, because then you're really just zooming in to the tops of the graphs, and it's going to amplify the difference in those different groups when really maybe those differences are more slight than they might appear, right? So this looks like a dramatic difference between these two, but really when you put 0 in the picture and you zoom out and you look at it from the proper perspective, you realize, there's not much difference between Honda Civic and Toyota Camry. All right. So again, Honda might want to give you this graph because it makes them look much better than Toyota Camry. But if we're trying to be honest with ourselves about what the data actually shows, this is the graph that we should look at. Some other things you have to be careful about with these two graphs. Here, there's nothing wrong with the bars being used here. They're accurately representing, the width of these bars really corresponds to these numbers. But it's just the fact that they're not plain bars, but it's a portion of a dollar bill, which just kind of distracts from the data that's being presented. So you don't want to add in things that would make it more difficult to interpret the data that's being presented. So that's something you want to be careful about. It's distracting. The other thing you want to be careful about, and what this graph is illustrating, is that we don't want to use three-dimensional objects to represent one-dimensional data, right? So this is the same data that's being referred to over here, and it's just cost. It's just salaries, I guess, not cost, but it's salaries, right? So the average salary of somebody with no high school diploma, the average salary of somebody with a high school diploma, et cetera, et cetera. This is one-dimensional data. It's just number, and we're just comparing $1 figure to another. Representing that one-dimensional data with three-dimensional boxes makes the difference more exaggerated than it really is. The thing with a cube is that if you increase, so for example, going from 18 to 51, let's use those two. 18 to 51 is it's a three-factor difference. So if I take 18, multiply it by 3, I get 54. So there's about a you make 3 times as much money with a bachelor's degree than you do with no high school diploma. That's what the data seems to show here. If you take the length of the side of this box and you triple it to reflect the fact that the difference here is it's a three-factor difference, tripling the length of the side of this box actually changes the volume of the box by 27, by a factor of 27, because the volume of a box is whatever the side of the box is to the third power. And so if the side of this box is S, and then I triple that, so now it's 3S, to find the volume now, I raise it to the third power, and I get 27S to the third power. So if this box has a volume of S to the third power, right, I hit the wrong button. I wanted to rewrite my 3 because it's such a horrible 3. Let's try that again. If this volume is S to the third power, this volume is going to be 27S to the third power. So while the difference in salary, I keep saying difference, but what's a better way to say it? The increase in salary is by a factor of 3. The increase in volume of these boxes is by a factor of 27, not 3. And so it's exaggerating that difference. It's exaggerating that factor. And so it's really misleading to use three-dimensional objects to represent one-dimensional data. It's okay to use three-dimensional objects to represent data that is three-dimensional, but not one-dimensional. So again, misleading in the difference between these two. All right, so here's some examples from the homework, and then we'll be done. Again, I apologize for the horrible length of the video. As I mentioned, when I do these in class, and now I usually don't use such a big data set, so that's one thing, but also I don't know what I'm doing wrong. I mean, I'm just like talking too much or spending too much time on a particular topic when I really probably could say half of what I said and move on and still get the point across, so I apologize. So this is a problem from your homework. In a study of retractions in biomedical journals, 470 were due to error, 189 were due to plagiarism, 827 were due to fraud, 296 were due to duplications of publications, and 272 had other causes. Construct a Pareto chart among such retractions. And I don't know why they use a comma there. Does misconduct appear to be a major factor? All right, so a Pareto chart, remember, is a bar graph. But the rule for a Pareto chart is that the bars need to go from highest to lowest. So C and D we can immediately eliminate as correct answers because they're not following that rule for a Pareto chart. They have to go highest bar to lowest bar. Now A and B go from highest to lowest, but obviously the issue there is that one of these, like this red bar, is much higher than this one. Now the blue bars look about the same. So I'm not going to be able to distinguish which answer is correct by looking at the blue category, which is the fraud category. So let's look at errors, number of errors. 470 are retracted due to error. This bar is below 300, so this one can't be correct. So A must be the proper option. And it wants to know, does misconduct appear to be a major factor in among such retractions? Okay, I guess I skipped that phrase. I was like, that's confusing why the comma's there, but I skipped that whole phrase. Construct a Pareto chart. That's what we just did. We picked the right one from the multiple choice. Among such retractions, does misconduct appear to be a major factor? So we have error, plagiarism, fraud, duplications, and other causes. So I don't know which one they're considering to be misconduct. I would be interested. I didn't capture it in my screen grab, but I would imagine that you're going to have like 4 options. 2 of them are going to say yes, 2 will say no. And you'd have to look at the wording to see what issue they're wanting you to probe. Now, if by misconduct they mean just plagiarism, that seems to be pretty low, relatively speaking, to the other issues that caused retractions. And so I would say no in that case. It's the least common reason. If misconduct means fraud, yes, that's a big issue. And so, yes, I mean, that's the number 1 issue is fraud. If it's those together, because those are both forms of misconduct. So again, it kind of depends what they mean by misconduct. And I think that would be explained in your multiple choice options, what they're really meaning by misconduct. So if they're meaning plagiarism only, then no. If they're meaning plagiarism with fraud, then yes, it's a major issue because it's the leading cause. Fraud is anyways. If they only mean fraud, then still the answer is yes, because that's the leading cause of retractions. And if they're meaning something else, because sometimes maybe the point is, well, it depends what you mean by misconduct. And it depends on the other issue that we don't, the other thing that concerned me a little bit. Oh, I'm sorry. I just need to read the question, don't I? Does misconduct, and they actually tell us here what they mean by misconduct, and I just didn't even see it. So duplication is misconduct. I didn't realize that, but yes, it does appear to be a major factor among the retractions. Misconduct is definitely a major factor because fraud is the leading cause. Duplication is fairly significant, and plagiarism, especially if you combine the 3 together, it's a really big reason why these retractions are happening. So yes, I would say the answer there should be yes. All right, so I just need to be done with this video. It's gone on for too long. So the given data represent the number of people from a town, aged 25 to 64, who subscribe to a certain print magazine. Construct a frequency polygon. Does the graph suggest that the distribution is skewed? So remember, we talked about skewed data with the histograms, and we also kind of mentioned it in the video for section 2.1. So we just need to kind of find which of these graphs seems to match the chart that we see here. We can rule out C immediately because it's not a polygon, right? You have to tie the ends down to the axes. These other 3 do that. We want to be using the midpoints. And so, I don't know, I just have a bad feeling about this one being at 65. That just doesn't seem like, I don't know, but maybe that is right actually, because it ends at 64, but we want the midpoints, right? So 65 would really seem to be maybe the boundary, which we don't want to use for the frequency polygon. So I'm saying B doesn't look right to me. The midpoint for this one's going to be somewhere around 60, and then the class width is 10, and so we want to go 10 away from 60, which would be 70. So this looks more correct to me. I don't know why I'm putting an X there, but this looks more correct to me as far as where we would expect that last point to show up, because it should be 10 away from the last class midpoint. And same thing with this one. So A or D are both in the running here. Now, if you look at the 4 classes that we have, the peak should be the 3rd class, whereas here, this is the 1st class, this is the 2nd class, this is the 3rd class. This frequency polygon peaks at the 2nd class. So that isn't correct. It should be peaking at the 3rd class, which is this one right here. So it looks like A is the right answer again. And does the graph suggest that the distribution is skewed? Yes, because we have a pretty big clump of data here to the right, and it seems to be pretty low to the left. It would not be skewed if it peaked in the middle and was the same to the left and to the right, or roughly the same. If this was lower, if this was lower down here, then I would say maybe it's not skewed. But because this one's almost as high as the peak, it really does seem to be skewed to the right. So I would say yes, it appears to be skewed. to the right or positively skewed was the description we talked about in section 2.3. All right, so does the distribution appear to be skewed? Yes. If so, how? To the right. All right, let's see. Hopefully one more example. Okay, this is the last one. The graph to the right compares teaching salaries of women and men at private colleges and universities. What impression does the graph create? Well, on first glance, it looks like men make a whole lot more money than women do by looking at the graph. And so that's what I would say initially. So let's see which option seems to cover that one. The graph creates the impression that men have salaries that are more than twice the salaries of women. That's a good point, right? This bar is twice as high as this one. So it does seem to indicate that men make twice as much as women if you're not careful about looking at this graph more closely. But let's just make sure the other options don't ring true. So the graph creates the impression that men and women have approximately the same salary. That's definitely not right. The graph creates the impression that women have salaries that are slightly higher. No, that's not even close. The graph creates the impression that men have salaries that are slightly higher than women. It's not slight. It doesn't look slight when you're initially looking at this graph. So A, again, is the right answer. Does the graph depict the data fairly? No. Why does it not depict the data fairly? Because it's not starting at 0, right? It's starting at, now this isn't a frequency so much as just like looking at salaries, but it's starting at 50,000. And if you zoomed out and started at 0, and let's say this is 10, 20, 30, 40, 50,000, 60,000, 70,000, right? Which is, no, we don't need to go any further than that. For women, they'd be between 50 and 60,000, which would be right here. For men, they're between 60 and 70,000. So there is a discrepancy. Men are making more than women. That's not disputable. But this graph is misleading, and it presents the difference, the discrepancy, more dramatically than it may otherwise appear if you compare it, you know, again, relative to 0. Relative to 50,000, this is a huge difference. Relative to 0, there's it's a more of a slight difference. Again, not to say that there isn't some issue there that needs maybe to be explored a little bit further. All right, so that is the end of the video for section 2.3. Again, I apologize for the length of these videos. Drawing the graphs takes time. I'm hoping with chapter 3, it's more calculation based. Hopefully we will be able to get through that material, and the videos will be a little bit shorter, starting with chapter 3. So I will see you in the next video, section 3.1.